So now what we want to do is talk about LC oscillations. So an LC oscillation you get when you have a capacitor that's charged up and you connect an inductor across it. So we have a capacitor and we have an inductor. So what happens is that the capacitor is going to want to try to discharge. So the current wants to flow. Now again, remember the electron flowing the other direction, but conventional current goes plus to minus. And so the electron want to flow the other way, but the current wants to discharge, and it goes through the capacitor. But what happens is that the capacitor doesn't like for current to change in it. So it resists the initial change, and so this means that it only slowly discharges at first. So then more current flows, then more current flows, then more current flows, until eventually the capacitor is discharged, but current is flowing as it's discharging. So once it's discharged, the inductor tries to keep current flowing even though the capacitor is discharged. And so current flows, and then you start ending up charging the capacitor in the other direction. And so once it's charged in the other direction, then the current wants to flow back this way. And so the current actually flows back and forth, and so the circuit oscillates. So current flows one way, and then it flows the other way, then it flows the first way, then it flows back the other way. And so current goes back and forth with a characteristic frequency that depends on the circuit elements themselves. And so this is sometimes called a tank circuit, because this sort of oscillation occurs anytime you have this capacitor inductor pair like this in a circuit. And so what we want to do is investigate this. So we have a capacitor, have an inductor. And so if we imagine the voltages here, this is charged here, and so we imagine a Kirchhoff loop here, so that we have that the voltage on the capacitor here, the voltage on the capacitor minus the voltage on the inductor has to equal 0. So that means that the Q over C minus the L di dt, well, except that in this case, the di dt here, okay, the di dt is going to be negative, so that will make that positive. So remember, it's minus L di dt, so we have to subtract the negative. And so there's our equation right there that we want to solve. So let's pull the derivative on one side of the equation. We have L di dt equals minus Q over C. So di dt equals minus 1 over LC times Q. Well, di dt, di is actually dq dt. So I is dq dt. So I equals dq dt. So that means that we have the second derivative of Q with respect to time equals minus 1 over LCQ. And so we want to solve that equation. Well, actually, we've sort of solved that equation in Physics 1. In Physics 1, if you remember, if we have an object on a spring, mass right here, if that's the equilibrium position, if we pull it away from the equilibrium position, there's a force on it. The force equals minus kx. And force equals ma minus kx, so a equals minus k over mx. So the second derivative of x respect to time equals minus k over mx. That's the harmonic oscillator equation. And so that's pretty much the same equation we have. You know, instead of x, we have q, and then these are just constants out there. So basically, the equation that we have for the charge is a harmonic oscillator equation. And so that means the charge is simply going to oscillate, and the charge will oscillate back and forth. And so that means this is a very analogous sort of thing. So second derivative of q respect to time squared equals minus 1 over LC times q. Okay, and so that's the equation that we have to solve. And so we say, well, what can we imagine this would be? Well, we know that something that if you take the second derivative of it, you get negative of the original. That is going to be a sine or a cosine. So if we assume we start off with a charged capacitor, then that means it's going to be a cosine because you already have charge on it at time 0. And so we would say that the Q is going to be some Q naught times cosine omega t. Now, if you take two derivatives of that, you have omega squared that comes out. So that would mean that omega squared equals 1 over LC. So that would mean that omega equals 1 over square root LC. Omega is 2 pi f. And so that would mean that the frequency of the oscillation is going to be 1 over 2 pi times square root, it'll be 1 over, the frequency is going to be 1 over 2 pi square root LC. And so that gives you the frequency of oscillation. So if you know the inductor and the capacitor, you can then find what frequency of oscillation you have. And so that gives you a resonance, because this circuit will naturally oscillate at that point. And you know from our discussion of harmonic oscillators in Physics 1 that if you have a harmonic oscillator that you add energy to at the resonant frequency that wants to oscillate at, you just increase the energy in the oscillator. When you increase the energy in the oscillator, you remember the energy in the oscillator from Physics 1, the energy in a harmonic oscillator is going to be basically 1/2 k x squared. And so you could then imagine, therefore, that the energy in the energy that is in the the energy that's going to be in the that's in this oscillator is going to be equal to q squared over 2c by analogy. And so that's going to be the energy in the oscillator, and so the more energy you put in there, then the more Q. The bigger the Q, because the current is dq dt, the bigger the Q, the bigger the current. So you could actually use this as a tuning circuit for a radio, either broadcasting or receiving, because if it's receiving, then an incoming signal of the right frequency would tend to make the oscillation simply get bigger and bigger. The frequency doesn't change. If you want to broadcast, then you drive it, and it's going to naturally drive at this frequency. So this is your tuning circuit. This is your basic tuning circuit right here. And so that's what these tank circuits tend to do. If you put a tank circuit in this little LC tank into any kind of circuit, it is going to inherently try to oscillate at a particular frequency.